similar right triangles. When you look at this picture, hopefully you see three triangles. There's the red triangle, which is the small one, the blue triangle, which is the medium one, and then the full thing together is what I call the big triangle. It turns out that those three triangles are similar, right? Well, this is why this section is kind of called similar right triangles. And if I move C in this GeoGebra app, that it's always going to keep that top angle 90 degrees. Okay, so there are three of them, and they are similar. Here's why they're similar. I'm going to prove to you using angle-angle. And we already know that angle-angle really just means that all three triangles have the same three angles, which means their sides are proportional, which means they're similar. So if you take a look at this bottom angle, let's say it's like 70 degrees. But if that's 70, the tiny one up top has to be 20. But if that's 20 and all of it together is 90, well, then the other one has to be 70. But if that's 70, then that has to be 20. So that means this triangle and this triangle both have to have a 90, a 20, and a 70-degree angle, which means the triangles are similar. And even look at the big triangle. It's got a 90 here, a 70 here, and a 20 here. They all are 20, 70, 90 triangles. And it doesn't matter what you make that angle. You can make it smaller, or you can even make it bigger and have it go off the screen. It doesn't matter. Whatever you make this angle A, it's the same thing up here for the blue part. Because this and the small one make 90, but that and this angle make 90, well, then those angles have to be the same, of course. Okay, so we do, in fact, have three similar triangles. We can even do this, and it's going to like separate them. Now, it goes off the screen because I don't really like how far it pushes that one up. I can make it a little smaller. And so you can kind of see it's got the small one, the medium one, and the big one. And when you hit the next, it's going to orient them around. So it puts them all in the same way. So in this way, they've oriented it so the hypotenuse is on the bottom for all of them. The short leg is right here, and the long leg is right there. And again, I'm going to reset it because I'd rather look at this blown up version. Okay, so for me, in the past, students have struggled with this the most. So we know we can set up proportions, right? We can say hypotenuse is to base, that's hypotenuse is to base. Or we can say long leg is to the short leg, and long leg is the short leg for any of the similar triangles. So let's just focus on the red, which is the small one, and the blue, which is the medium triangle. So what if I wanted to say hypotenuse is to the long leg? Okay, so for the red, we would say B is to E, so B over E is A over G. Hypotenuse is to long leg as hypotenuse is to long leg. Okay, that makes sense. Let's say I wanted to do long leg to the short leg. This is where it gets a little tricky because of E. E is the long leg of the red triangle, so E over F is equal to G over E. The weird part is, again, focus, E is the long leg of the red triangle, and it's the short leg of the blue triangle. So E can actually be in both proportions because E is a shared side for both the small and the medium triangle. So you have to be careful on that. Let's say I was looking at the blue triangle and then the big triangle, triangle ACB. And I could do something like A is to G, hypotenuse is to the long leg, and then what's the hypotenuse of the whole thing? Well, it's G plus F, or I think they just call that C, is to A. You see how I used A in both of those cases? If I'm doing hypotenuse to long leg, A is to G, as C is to A. Again, A would appear in both things because A is the long leg of the big triangle and the hypotenuse of the medium triangle. Just like B is the hypotenuse of the red triangle and it's the short leg of the big triangle. We're going to set up proportions to solve for missing variables. We can set up proportions because we know the triangles are similar, and we know the triangles are similar because of angle-angle. All right, we're back again with similar right triangles, and I've drawn the three of them up here. So we have the small triangle here, BCD. We have the medium triangle here, but again, I gotta flip it, I got to rotate it up and down so it matches the same orientation. Just remember, this dotted line here, this BC line, is the long leg of the small triangle, but it is the base, it's the short leg of the medium triangle, so I had to flip it. And then this side, BD is the short leg. There's the long leg of the big triangle, and of course that whole thing is the hypotenuse. Okay, and so AD is the hypotenuse of the big one, AB is the hypotenuse of the medium one, and then BD is the hypotenuse of the small one. And so we can set all these proportions, just to make clear. Angle B, the measure of both of those, this plus this does equal 90. That is a 90-degree angle up there, which is why all of them are right triangles. A BC is what we call the altitude of the big triangle, but again, we have a small, a medium, and a large one, and because of that, we can set up proportions. Okay, and I'm going to do that by just looking at some problems. Okay, let's say I wanted to solve for all of these variables, x, y, and z. And x is the hypotenuse of the small one. It's also the short leg of the big triangle. Y is the hypotenuse of the medium triangle. It's also the long leg of the big triangle. And then z is the long leg of the medium triangle. And again, we are talking about a right angle there, and of course dropping an altitude makes that a right angle. Okay, so how do you want to set it up? Let's look at the small triangle and compare it to the medium triangle. Okay, so for the small triangle, I'm going to say the long leg is to the short leg, and then I'm going to go to the medium triangle, I'm going to do the same thing. The long leg is to the short leg. Oh shoot, that's the 12. Okay, say that again. Look at the small triangle. Long leg is to short leg as long leg is to short leg. Okay, then I'm going to solve this. Solving this, I'd get 144 equals 5z. Oh man, I didn't do that ahead of time. 144 divided by 5, so that's going to be, I guess I'm going to need my calculator out for the next part anyways, because y and z may just be decimals, right? So I don't want to actually mess that up. So I'm going to get 28.8. So z is 28.8. So I know that length now. Okay, and at this point, if you actually don't want to do any more proportions, you could just use the Pythagorean theorem, because I could do 5 squared plus 12 squared equals x squared. All right, I could do that. I could do 12 squared plus 28.8 squared equals y squared. So I could actually solve for x and y and not even use anything else, okay? So I could say 5 squared plus 12 squared equals x squared. 25, 144 equals x squared. That's 169 is x squared, and you're like, oh, boom, 13. All right, I made that one work out nice. That's actually a Pythagorean triple. Okay, let's do it different this time. Let's actually use proportions to solve for y, just for fun. Okay, let's look at the small, and then we'll look at the big. All right, let's check this out. Let's say 13 is to 5. So what did I do there? Hypotenuse is to the small base. As the big triangle, oh no, I gotta say 12. That was silly. 12. 13 is the long leg as the hypotenuse, which is 33.8, is to y. Again, I had to make that switch because y is the long leg of the big triangle. Okay, so then I just solve. 13y equals, and I'm going to get 33.8 times 12, 405.6, and then I'm going to divide by 13. And I'm going to get y equals 31.2. Let's check our answer. Let's say we did it differently. Like, oh, okay. Well, couldn't I have said over here that 12 squared plus 28.8 squared equals y squared? So if you do that, you get 144 plus 28.8 squared is 829.44 equals y squared. Add those together and then take a square root. And of course you get the same thing. So whether you want to set up proportions or whether you want to use Pythagorean theorem, it's totally fine. Usually you have to use proportions at least once. And again, this one, I was comparing the small triangle to the medium triangle. Over here, I was comparing the small triangle to the big triangle. And it doesn't always even matter what direction you want to go. Okay, let's do this one. Let's do small and medium first. So I'm going to look at this triangle versus that triangle. Okay, so I'm going to look at the small one, and I'm going to look at the medium one. Okay, if I look at the small triangle, I'm going to say long leg is to short leg. And I'm going to look at the medium triangle. Long leg is to short leg. All right, makes sense. Long leg is a short leg as long leg is a short leg. They have to be in the same ratio because they're similar triangles. Well, now I'm going to get x squared equals 4 times 9 is 36, and I take a square root and I get 6. And you're like, sweet, I know that value is 6. Well, if you know that's 6, then actually it's probably pretty easy to find y, because I can just use the Pythagorean theorem. 6 squared plus 4 squared equals y squared. 36, 16, 52 equals y squared. So y equals the square root of 52, and actually I can even break that down exact if I wanted to, because that's 4 times 13, and I get 2 square root of 13. As a decimal, if that's what you were looking for, 2 square root of 13 is right around 7.21. Okay? And if I wanted z, I could do the same thing. I could say 6 squared plus 9 squared equals z squared. And that would just be 6 squared plus 9 squared, then take a square root of 117 and get around 10.82. Okay, so I would know x, I would know y, and I would know z. Again, setting up the proportions is the hardest thing, and you don't always have to compare the small or the medium triangle. You can look at the small triangle versus the medium triangle versus the big triangle. You can compare the legs. You can compare the hypotenuse to a leg. And again, you're keeping track of what's what. And again, this is the small leg of the small triangle. This is the big leg of the small triangle. This is the hypotenuse of the small triangle. And the hard part is when you go to the medium triangle, this 12 is now the short leg. This is the long leg. That's the hypotenuse. When you look at the big triangle, this is the short leg, this is the long leg, and this is the hypotenuse. And so when you set up the ratios, you just have to be careful. This is the kind of classic example where I used x, which is the altitude. X is in both of them, because for the small triangle, it was the big leg. For the medium triangle, it was the short leg, which is why it's up, and then it was actually down in here. And again, this is where like even the geometric mean term comes into play. Okay, so hopefully, these two examples and then the GeoGebra app kind of give you an idea of how to set up similar right triangle problems.